Hello, and welcome to Unnatural Numbers, the YouTube chat show where we take divine mathematics and put it in the mouths of mere mortals. I'm your host, Benjamin Cornish, and today I'm joined by two fabulous guests. Returning to the show for, I think, the third time, we have Christian, who is the Mega Grant winner, not the MAGA Grant winner, the Mega Grant winner, which is a grant in promoting mathematics in public. And he is doing the Beach Spectre project. I'm sure he wants to talk to you more about that at the end of the episode. And he's coming up to us from Newcastle. And we also have Khensanii, who is an enthusiast in mathematics and computer science, joining us from South Africa. Hello to both of you.
Hello.
Hello.
So coming in with fact number one, we have Christian. Christian, what's your fact for today?
Actually, I want to give you two facts, if that's all right, if I can have just
Absolutely.
time, because this is number 7, and you said, does anyone want to do number 7? I said, yes, there's absolutely tons of facts about number 7. So I've got a good one later on, but really, the thing about number 7 that you remember, that everybody will remember, is to do with the digits of 1/7. Do you know the recurring digits of 1/7?
Yeah, so in decimal, we're talking something like 0.14145, something like that. For 2.
Now, right, so 142. And I'm not going to make you do the sum because this is the quick thing I want to get out of the way before I do the real thing. Okay, so, and it repeats, right? So you know what do you do? You're a teacher, you do little dots above the digits where it repeats.
Mm-hmm.
Right. How do you remember? Oh, I've got one. I think it's all the way over there. There we go. How do you remember what those digits are?
Well, it's just all the digits between 1 and 9, apart from a couple of them in some random order. Everyone knows that.
Exactly. I mean, that's like a photo fit description. You may catch the digits of 1/7 on the street that way, but you wouldn't hang it up in their living room. Okay, so these digits, they've got some really interesting properties. Did you know that 1/7, or the digits of 1/7, this is the only cyclic number in base 10?
Really?
By which I mean, so...
What about 1/3?
Right, so the property I want is, that's not a great 7, is it? 1/7 is that. 2/7, do you know what 2/7 is?
Oh, this is the one that starts at 2. So it'll be 0.2, is 0.2, and then probably 8, because you're doubling the 4, and then double the 2 is 5.
Okay. Can you see a pattern?
Yeah, well, it's a skip pattern, isn't it? It's all shuffled down.
Yep. So 3/7, let's add these things up. 0.4. Actually, all I need to know is the first one. I'm telling you that this is true.
Mm-hmm.
So the multiples of 1/7 are all just cyclic permutations of those digits.
Right.
So that's an interesting fact. That's the only number that works for in base 10.
Oh, right. So 1/3 does have a repeating pattern,
So
but
1/3
isn't the same pattern.
Yeah. So 2/3 is not a permutation of those. It's something else.
Yeah.
Okay.
Well, hang on. That cyclic pattern doesn't always work, does it? What about 7/7?
So 7/7, you get back to 1. Yeah.
Yeah. So it's very nearly cyclic.
Very nearly, very nearly.
Yeah.
Well, all the ones you'd want to get more than period 7 out of that, given that it's 6 digits long, would be notable. That's how I would describe it. Okay, so but the other thing that someone recently told me is this: split the digits in 2. 1, 4, 2, and 8, 5, 7. What do those add up to?
Oh, 999.
9, 9, 9. That's how you remember the digits.
Right.
So you remember that it's 0.14 something something.
Wait, okay. I mean, you're still going to get the 142, and that's not quite all of the even numbers or in any kind of sensible pattern, is it?
Oh, like I mean that's easier than remembering all six. I can never remember exactly which way round they go, but since I learned
Yeah,
this fact, I can write this down reliably. So that's the thing about that's digits one
that's
over
pretty
six.
cool.
So there you go.
I mean, that's great. I mean, to be honest, I did know the fact before. I would not back myself to write them down reliably. If you got in a bar fight with me over the cyclic digits of seven, I would not have that fight.
Exactly. Me too. A few months ago, I was the same, but my life has changed now that I know this
And
fact.
now, and now you will have that bar fight.
I will. I will have it with gusto. Right. So that was my first thing. Okay. Right. So do you want to know something else about the number seven?
Hmm.
So here are my friends, the Seven Dwarfs.
Yep.
Got three copies of them. Can't think of a reason why. I'm just going to tell you I've got three copies of them.
Okay.
So I want to group up these dwarves into groups of three. I want to have three different dwarfs in each group.
Is this just a game for me to try?
Yep, you can try it.
Okay. Well, I reckon if I draw a diagonal line, that guarantees a three,
Mm-hmm.
and then I could do it like this, right? And that's going
Yeah,
to guarantee I have three in each group.
that works very nicely.
Okay.
So you are one of the, I don't know what proportion of people, when I give them this puzzle, some people just immediately come up with this solution. Others, and I'm glad you are because we didn't have very long to do this.
No, yeah.
Others will spend 10 minutes, any amount of time trying to do this, shuffling pieces around.
Well, if
Um,
you give them counters, they're going to want to shuffle them around, aren't they?
yeah, yeah. Well, except I have this as a puzzle that I use for like open days and things. So we have all these counters out on the table, and some people will arrange them into those rows like that and go da, 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 systematically. So that's not the solution that I use when I do this. Okay, so I've taken three copies of whatever that dwarf is. I should have remembered. I thought, should I remember the names before this so that I can just say Grumpy, Doc, whatever? But I didn't. So I've arranged three of them in a line. What I'm going to do next is put different ones on a different line.
But you're happy with those two being on, are they on the same dot?
Yeah, so these two here are going to be in part of the same group.
Okay. Oh, I see. Okay.
And then I'm going to put some more in yet another line. And a shape is starting to appear.
Triangle.
Triangle with a thing in the middle.
Ooh.
Mm. So what's next?
Centered triangle.
Center triangle. I'm going to try this line. Now, I'm about 50-50 on getting this right, so we'll see. We'll try that. There we go. So that these things are filling up. That's forced.
Is there an order to choosing your lines, or is it
There
random?
somewhat is. Now, somewhere it needs a blue. Hang on, let's do this. You need a red. You need a blue. You need a yellow. Right, I have done. You've spotted the triangle. I've pointed out the
Yeah.
point in the middle.
Can I draw the lines on? Because I'm struggling to
Yeah,
visualize
go
it.
for it.
So I think I can see one line here, one line here, one line there. Those are sneaky ones. But
Yeah,
then, of course, you've got the sides of the triangle.
yeah.
I'm sorry, you're all out of lines.
There's another line. There are three groups that are not finished yet.
Uh, yeah, but they're not in a line.
Don't worry about it. Just say that's a line. Here we go. Here's a line.
Okay.
It's my kind of line. Anyway, these groups need to have some extra things, and here we go. So I've done it. Right. So what I've made there is the Fano plane,
Okay.
which I know you've heard of because you've asked me to talk about the Fano plane. Um,
Yeah. So the how many lines are there in total? We've got one, two, three, four, five, six. Oh, I mean, you could have guessed because it's today's episode, isn't it? You've got seven lines.
7 lines, yeah. One of the lines to our Euclidean eyes looks a bit curvy, a bit circular, but no, don't worry about it. It's just the same as all the other lines. It's got 3 things on it. Each of the points on it is on 2 other lines. It works just the same as all the other lines. So this is an example of a projective plane. And I'll say why it's a projective plane. Do you want to guess why it's called a projective plane?
Oh, no, no, I've genuinely struggled with the etymology of that for years.
Okay. So I'm gonna move down a bit. I'm gonna draw you a
So,
picture.
because I thought a projective plane was to do with like shadows, and when you like make one thing that's multiple dimensions appear on something that's not got the same number of dimensions.
Yeah, yeah. So this is the finite version of a projective plane. Everybody gets taught how to do this, how to draw like a 1-point projection. So you pick a point that's like at infinity,
Hmm.
and then you draw lines out of it, and those are all at the same sort of height. This looks like a projection of 3D space onto the flat piece of paper.
Yeah.
What we've done is we've taken these lines, which are parallel, and in the real world, those will never meet. That's one of our axioms of Euclidean geometry. But we say in the projection, they meet at infinity, this point that doesn't really exist, but let's add it. Let's make it exist.
Hmm.
So all lines meet somewhere. So in a projective plane that's continuous like this, we sort of add 1 point at infinity and these things meet. In a finite geometry, we only have a finite number of points. So in this finite projective geometry, we've got a load of lines. Every pair of lines meets somewhere at a point, but otherwise, the ways that lines and points and distances between lines work is sort of the same. I can take any 2 points, maybe these 2, and draw a line on from them to get another point.
Hang on, let me say that again. So every 2 points will there for every 2 points there exists a third point that is collinear.
Yeah.
Do,
Yeah.
are
Why
the
not?
lines still all parallel to each other?
Well, okay. What does parallel mean? I had this discussion with primary kids. I went into 3 different primary schools last week and had lots of discussions about parallel.
Hmm.
What do you think parallel means?
I mean, I'm old school Euclidean, so I'd say t two lines that, when continued infinitely, they never touch.
Right. Um, or you could say that they go in the same direction.
Yeah, I suppose.
So it's hard to see here. Well, definitely they do touch. That's the projective part. And any
Hmm.
2 lines you pick touch somewhere. Um, so it doesn't quite the word parallel doesn't quite work here. The property I'm trying to remember is any 2 points have a unique line going through them. So
Oh,
there's only one line with these two groups on it. Um,
and that's another Euclidean really important property of a line. The line is always the shortest distance between 2 points, and it's unique.
yeah, the uniqueness part is the bit that happens here. Where that doesn't happen maybe is in hyperbolic geometry. You get lots of lines going through the same point. Yeah, hyperbolic geometry, you've got too many parallel lines. Spherical geometry, you don't have enough. Um, so yeah, this is the Fano plane. There's another interesting fact about this, as a thing about it, which is that it is its own dual. You can swap points and lines, and you have the same structure. So just like every every point is on 3 lines, every line has 3 points on it.
Oh yeah. If you were to view it as a graph, like a graph theory graph.
Yeah, so the graph dual of this is itself, which is interesting. That's true of any finite projective plane.
Oh, right, okay. So what makes this one a special one then, if that's true for all finite projective planes?
Well, they're hard to come by. um, so yeah, they're very hard to come by. This is the smallest finite projective plane. It's got
Ah,
it's got 7 points. You can't make one using fewer than 7 points.
can you make it? Does there always exist one for more than 7 points?
No.
Oh, okay. So it's a small set of.
Yeah, it's and I'm not actually sure if we know a general way of coming up with them. The next one up, you will recognize. Oh, I meant to prepare it. Dobble or spot it in America. So, in order to get your head around how that works, this is the point where we make the link with the dwarves. This is why I had the dwarves out. So each point here has 3 dwarves on it. Imagine that's like a double card. So there you go. There's my double card. Here's another one. Here we go. Any 2 cards that I pick have 1 dwarf in common. Can you see why?
Because that's how you laid them out. They were just the same dwarf but colored differently. That was the design of it.
That was the design. Yeah, design is a really good word. This is a block design. These kinds of things where you lay things out, they have however many things in common as a rule. That's called a block design. It's really important in things like designing experiments so that you can control for different factors. If you've got a finite number of things and multiple conditions you want to apply to them or different ways that they can vary, you can arrange things following a block design so that you cover all of your possibilities. Right. So because I've laid these out this way, you can see that any 2 cards lie on a line. And when I constructed it, each line was a different dwarf. I think Grumpy is here. He's down here and he's here. And he's also in yellow, hiding behind them all up there. So that's the Grumpy line. So because we know that every line is 1 dwarf, and that thing about there being a unique line between any 2 points, we know that for any 2 cards that I pick, there will be exactly 1 dwarf that they have in common. Never more than 1, never less than 1. But there you go. That's the Fano plane.
Yeah, that's really good. That's a lot easier to understand than when I was desperately trying to read the Wikipedia article earlier. Do you want to can we try playing noughts and crosses?
Yeah, go for it.
Yeah. Okay, I'm going to get rid of the lines to make it harder for us both. Can I start?
Yeah.
Because I've been planning my strategy. So I'm going to take the top one. Although it doesn't really matter where I start because am I right in thinking the Fano plane looks the same, as in you can invert it and it's always the same?
Yeah, exactly. So one thing I didn't mention was that its automorphism group is pretty big. It's got loads of symmetries. Is the short way it's the more understandable way of saying that. Yeah, you can swap pretty much anything around.
You've gone there, so I'm going to go. I can't go here. I think I want to go over here.
Okay, so the property of the Fano plane that's interesting is that for any 2 points, the next one in the line is determined.
Yeah.
So
that means this game is actually really, really boring.
Yeah, so as soon as you get 2 in a row, I can just knock off the other one.
But oh no, so I automatically always get. If you start, you'll always win.
Yep.
Oh, that's the kind of game I like. Oh, thank you very much, Christian. That's great.
There you go.
Thank you very much, Christian. That was lovely. So for our next fact today is me. And my fact today is all about the regular heptagon. So that is a 7-sided shape. And I'm going to be answering the question, can we construct a regular heptagon? And the answer is, of course, yes, there's one. I did it just there. Although I constructed that using GeoGebra. So what about if we want to go to Euclidean definitions of constructability? And this is something that I imagine most people try when they are at school. This is using the pair of compasses and a straight edge. So these are the only tools that the ancient Greeks allowed themselves for a pure construction. If you could do it with just these two tools, we'd say it is a static geometry and it's okay. If you need to use other tools, it's not good enough. So can the regular heptagon be drawn just with these two implements? Well, that's where things get a little bit trickier. And to answer that question, I think we need to investigate some more about the heptagon and also about what these two tools are capable of. So these two tools, let's look at the straight edge first of all. The straight edge will connect any 2 points and then connect another point that is in a straight line with that point. In other words, that gives us a way of creating and solving linear equations. So the pair of compasses draws a circle. Now the equation for a circle is x squared plus y squared equals r squared, or you could define it differently in ancient Greek, but it effectively gets all of the points that are the same distance, Pythagorean distance, away from another known point. And in that way, it's kind of like solving a quadratic equation. So these two tools are the ancient Greeks' way of solving quadratics and linear equations. So on this heptagon, can I construct this with just those two types of equation? Well, here I've drawn on one line of my heptagon from the center out to an edge. And just for the sake of ease, I've said that is a length of 1. So we might call this the radius of the heptagon is 1. And then I've taken another line that is a perpendicular bisector of one of the sides. And I want to calculate the length of that line there. So here we have a right-angled triangle, which is convenient for us because that means we can use trigonometry. If I think about how many of these angles I might find in the regular heptagon, you could say that this angle here is pi over 7. Notice I'm using radians here, where the total angle inside the whole circle might be 2 pi. And then there are 14 of these little half triangles, and that gives us pi over 7. So therefore, in order to calculate this length, I need to use trigonometry, and I could say that this is actually equal to the cosine of pi over 7. If the other length is 1, this one must be cos pi over 7. So my question is now going to be, can I find the value of cos pi over 7 using quadratics and straight lines? Now, your first thought might be, of course you can't, that would be ridiculous. But remember that there are some values of sine and cosine that are actually really easy to represent in terms of Pythagorean lengths, in terms of quadratics or straight lines. Consider, for instance, cos of pi over 3 is just equal to 1/2, and that can be expressed using linear and quadratics. So let's think about whether I can do cos pi over 7. Okay, so in order to answer this question, I now need to introduce a new tool of mathematics, which I think is possibly one of the most undervalued things that never gets taught to undergrads, and that is the Chebyshev polynomials. So the Chebyshev polynomials are a class of polynomial that look a bit like this. So they're a whole group of them, and they are recursively defined, which means each polynomial is defined by previous polynomials in the sequence. And they create a sequence that looks a bit like this. And you might recognize them to be maybe a little bit like the cos graph, if you squint a bit. Let's first of all see how we might define these more formally. So the Chebyshev polynomials, the first one we just say is 1. The next one is x. But then after that, every new polynomial in the sequence is going to be 2x times the previous one, subtract the one before that. So it's got a bit of a Fibonacci vibe going on, but we're making a sequence of polynomials, a sequence of functions. I think it's beautiful. And using just these simple rules, these 2 starting points and then this one recursive pattern, we can create as many Chebyshev polynomials as we want, up to whatever order we want. Now, the next point, I'm going to have to just tell you as a fact, because this is a little bit over my head, the justification of why this is. But the point of using Chebyshev polynomials is they have this property. So the property is, take a Chebyshev polynomial to the nth order, so the nth one in the sequence, and multiply it by cos theta. That's going to give you the same value as cos n theta. And this is where you might have noticed that the somewhat cosine-esque pattern of these polynomials comes in handy. It's almost like having a polynomial that is being squeezed, hence the cos n theta. So that's the property that we're going to make use of. So how does that relate to what we were talking about before with the length that we were trying to construct on the regular heptagon? Well, we want cos of pi over 7. So let's see what happens then if we want to take cos of pi over 7 on the left-hand side here and multiply it by the 7th Chebyshev polynomial. So we have the 7th Chebyshev polynomial, T7, multiplied by cos of pi over 7. Well, this is going to be equal to cos of 7 times pi over 7, which is just going to be equal to cos of pi. And as everybody knows, cos of pi is just equal to -1. So let's have a quick look at the 7th Chebyshev polynomial. I won't derive it, but you can do the arithmetic yourself if you really want to. I'm going to shortcut to the answer. There it is, the 7th Chebyshev polynomial. And what we're saying is if we substitute in cos of pi over 7 into this polynomial, the result will be -1. And in that sense, we're trying to solve the equation that 64y to the power of 7, take away 112y to the power of 5, plus 56y to the power of 3, take away 7y, plus 1 is equal to 0. Well, now the game is afoot. We want to solve this 7th order polynomial using just a compass and a square edge. Now the compass will do things that are to the power of 2, it will do quadratics. The straight edge will do linear equations. Can I turn this into a problem that only involves quadratic and linear equations? It looks like you might not be able to because of that power of 7, but remember we can use them recursively. I can do quadratics of quadratics. So can I make a power of 7 just using quadratics of quadratics? Well, let's just factorize that. I won't patronize anyone. I'm sure you can all do the factorization in your head, but I'll give it to you here. So we factorize it into the three factors, x plus 1, 8x cubed, take away 4x squared, take away 4x plus 1 squared, equals 0. This part in the middle, the 8x cubed, take away 4x squared, take away 4x plus 1, is what you might call the minimally reduced polynomial. It's the smallest value that we can get, having taken away all of the unnecessary factors. And what do you know? It is a cubic equation. Therefore, in order to construct a regular heptagon, we need to be able to solve a cubic equation, but the tools that we use can only go up to quadratic equations. And therefore, because we can't resolve it to a quadratic equation, it cannot be constructed with a pair of compasses and a straight edge. There's my fact. And I'll go one step further and say 7 is the first polynomial that cannot be constructed with these tools.
So I just think that's really interesting that you needed to know so many things there. You needed to know those Chebyshev polynomials. That could just be the way that you've done this particular proof. But the link between a geometric drawing and equations was really quite late on.
Mm-hmm.
And then sort of from the point at which people made that link, that's when the explosion in understanding algebra and which equations can be solved and which can't really was. So yeah,
I mean, of course, the link between the algebra and the geometric construction didn't come till much later after Euclid's time. I think it was Descartes who really introduced the idea of using these algebraic variables to jump off of the old Greek geometry, and that was, I think, the 1600s. Chebyshev polynomials came in 1856, so it was knowable from then. Although the Chebyshev polynomials aren't exclusively used for this, they're also really useful in differential equations and a whole load of other areas. So I still don't have the answer of when did we know this was not done.
That's fine. What's really interesting is that would someone like Euclid have been happy with this proof that it's not constructible? And it's a real thing that had to happen, that mathematicians who were used to doing geometry and talking about squares literally as squares, that kind of thing, allowing themselves to use tools of algebra which don't feel quite as nice, maybe, to prove things about geometry. And this is something that happens over and over in maths, that you have some other way of looking at something that maybe doesn't feel quite as nice, but gives you some good theorems. And you sort of have to say, okay, well, yeah, okay, you've proved the thing. And is that the proof? Is that a nice proof of it? Or do you want to say, okay, well, now we've settled it, let's keep looking for the purely straight edge and compass
So,
proof of
so
this?
this is I mean, you'd be right to notice that Euclid would not have been happy with this, and that's partly because I asked you to take it on trust that this line here was true, and I've admitted any kind of justification for that. But here, I'm gonna go to an Archimedean style of proof, and that is the method. That is the capital T, capital M, the method of Archimedes, where he liked to first intuit something. So just going on vibes alone, and then once he was satisfied that the vibes were correct, then he'd go back and find the rigorous proof afterwards. So I think Archimedes would have been very happy with the vibes of this problem, and then after that, probably used weights and measures and levers to try and figure out the actual proof. Breaking news. We've just discovered when the regular heptagon was known to be non-constructible, and it was 1837. So that's only about 20 years before the Chebyshev polynomials came along in 1856. That means that there exists another proof for it that does not involve this method that someone else can go and present on instead.
This is the nice proof, is it?
It's the first one I came across.
Yeah.
So there we go. Anyway, that's me done. Lovely. Up next then for our third fact, we're going to head over to Khensanii. Khensanii, what's your fact today?
So thank you once more. Since I'll be using PowerPoint, allow me to share my screen. I came across this quote right here, which says this number is the only prime number preceding a cube. Now, I found this line very interesting. I thought I should just elaborate a little bit on it.
Why is 7 the only prime of the form n cubed minus 1? Now this form n cubed minus 1 always factors like open parenthesis n minus 1, close it, then another open parenthesis n squared plus n plus 1, close it. Now if a number is a prime, it cannot be written as a product of two numbers unless one of them is 1. So for n cubed minus 1 to be prime, one of the factors must be 1. And the only way that happens is if n minus 1 equals to 1. Therefore, we can conclude that n will be equals to 2. Then you plug that 2 in that form, n cubed minus 1, which will make it 2 cubed minus 1. And 2 cubed minus 1 is 8 minus 1, which is equals to 7. Now, you can conclude that 7 is a prime. So, for any other n greater than 2, both factors n minus 1 and n squared plus n plus 1 are bigger than 1. So, their product is not a prime. Therefore, 7 is the only prime you can get from n cubed minus 1.
This kind of looks familiar to me. It looks very familiar. Hence, I think I think it's safe to conclude that 7 is a what? Is a Mersenne prime. And by Mersenne prime, we mean prime numbers of the form 2 to the exponent n minus n, where what? Where n is also a prime number. So yes, we said that 7 is of this form. Good. So now, moving on, they say it is a double Mersenne prime. Because why? Because 3 is a Mersenne prime. Now, back to that mathematical expression. They say 7 is a double what? Mersenne because 3 is a what? Is a Mersenne prime. How about we try writing down these Mersenne primes? So, I'm writing this because we said all Mersennes are of the form 2 to the exponent and n minus 1. So, yes. So what is 2 to the exponent 1 is 2. 2 minus 1 is what? Is 1. 2 to the exponent 4 is 2 to the exponent 2 is 4. 4 minus 1 is 3. And 2 to the exponent 3 is 3. I mean, it's, sorry. 2 to the exponent 3 is 8 minus 1 is 7. Now, this is our system of Mersenne primes and so forth. Yeah. Now, they say that 3 is a Mersenne prime, and we've just proved it right here. Now, what is a double Mersenne? These numbers are denoted by this formula or are of this formula. Where this is a what? Is a Mersenne prime, and also this whole expression is a Mersenne, which makes it what? Double. And then now, another fact is that this number is an exponent of a Mersenne prime. Now, I only gave you a few Mersennes, 1, 3, 7, and I said so forth. Now let us try finding out what is that Mersenne prime that is said that 7 is its exponent. Now we said Mersennes are what? Are of this formula 2n minus 1. And then we're trying to find out this number, which is said to be a what? A Mersenne. Now they say 7 is a what? Is an exponent. 2 to the exponent 7 minus 1. What is the answer? I think the answer is 127 if I'm not lying. Yeah, 127. So yes, it is an exponent of a Mersenne. So we have just proved that this prime here is an exponent of a Mersenne.
Okay, and that brings us on to the next segment of our show, and that is when we talk about the OEIS, the Online Encyclopedia of Integer Sequences. Today for our sequence, we've gone for a classic A005670, or as its friends call it, Mrs. Perkins' quilt. So the Mrs. Perkins' quilt sequence is generated by counting how many segments of quilt are needed to make a larger duvet cover. So Mrs. Perkins is doing some sewing and she wants to create a large square quilt out of smaller squares. And she asks herself, what's the smallest number of patches needed in order to construct the larger quilt? And then the sequence grows by 1 unit on the side length each time. So for a 1 by 1 quilt, 1 meter by 1 meter quilt, she's only going to need the 1 square, and that is a 1 by 1 square. But if she has a square that is 2 meters by 2 meters, she'll need 4 individual squares, each of which are a 1 by 1. Those are the first 2 terms of the sequence. So my challenge for our guest today is to try to work out how many extra squares are needed for the next 2 numbers in the sequence. Now, there is another condition that I've not informed you of, and that condition is the squares that make up the inside of the patchwork have to have a greatest common divisor of 1 with all of the other squares that are involved. So for our 3 by 3, we can't have any squares that are a factor of 3, which is easy enough because 3 is a prime number. But for Christian's challenge of the 4 by 4, he's not allowed to use any squares that have a side length of 2, because of course 2 is a factor of 4. Okay, let's have a change of pace. I'm going to do the 3 by 3, and then I'm going to get Khensanii to do the 4 by 4, and we'll make Christian do the 5 by 5. So looking at the 3 by 3, this one, I think I can do this in 6 squares. Let's see how I could make this using only 6 squares. I think I've got 1 2 by 2 square here in the corner, and we're going to just pretend that my sewing is as good as my colouring. And then I'm going to have 1 2 3 4 5 squares that are a 1 by 1. So if I was to record the different patches that I've used, I have used 5 lots of 1 by 1, and I've also used 1 lot of a 2 by 2. So in total, that is 6 patches are needed to cover a 3 by 3 quilt.
Very good.
So Khensanii, have a look at the 4 by 4. What do you think is the fewest number of patches you would need to make a 4 by 4 quilt? So the emergency escape hatch has been pulled. So the way that we might do it is we would take a 3 by 3 here. That would be 1 square. And then you could have 1 2 3 4 5 6 7. And that is the most efficient way to make a 4 by 4, using 1 3 by 3, and then 1 2 3 4 5 6. Hang on. Have I made a mistake there? Because I think the answer should be 7. 1, 2, 3, 4, 5, 6, 7, 8. How have I got 8?
Yeah, I got 8.
So it's got to be the smallest co-prime dissection of an n by n square. And are we confident we know what it's co-prime to?
So I don't know where the co-prime bit has come in. Where's that?
It's in the definition at the top.
GCD
Smallest co-prime
So
dissection.
it's the greatest common divisor of all of the sides. So you can't, for this 4x4, you can't divide it into all 2x2 pieces. But you can have 3
I
copies of
can
a
use
2x2.
2x2s. Right. Okay, in which case, Khensanii, are you ready for the, the corrected answer here? So that was my bad. I misinterpreted the question. So we are allowed to use some 2x2s as long as there is at least one that is not a 2x2. We should be on safe ground. Well done, Christian. Save the day. So we could have 1, 2, 3, and then these have to be 1x1s. So, Christian, I wonder, have you been able to come up with the answer for a 5x5 grid?
Incredibly, I think I might have. Let's see if we can do it.
Would you like to have a go?
The point is, I don't want to have some big number that divides the sides of all of my pieces. And because we're starting with more pieces here, I'm going to have some 1x1s. So I think I want to have a 3x3 there. If I'd had a 4x4, I would have just had to use 1s all around the edge. This wouldn't be the kind of puzzle you talk about if that was the solution. So I've got to fill in the rest. I can use 2x2s. So already, because I've got a 3x3 and a 2x2, their greatest common divisor is 1. So I can do what I like now. So I'm going to try and fit in as many more 2x2s as I can. I can't fit any more 3s. And I've got to put some 1s in on the end there. So I reckon 8, Ben.
Do you think the next number in the sequence is an 8? Should we have a look? Oh, it is an 8. Yeah, this is an incredibly slow growing sequence. It's one of those boring ones that is tedious yet really fun to have a go at solving. One of the things I love about these types of sequences as well is someone came up with the problem originally and they would have maybe found the first 5 or 6 numbers by hand and they would have had no idea if their answers were correct. Because once you get past maybe the 6 or 7 sides, the number of different options of arranging these squares becomes too numerous to check by hand. So if someone had a really good idea, and it would have taken possibly years before their answers were validated or possibly even corrected. So I quite like these types of sequences. It's a fun puzzle. I think the original one in the book where it was published was to do it for a 13 by 13 grid. So we'll leave that as an exercise for the reader. But that's Mrs. Perkins' quilt. And so that sadly brings us to the final segment of today's show, where we say thank you and goodbye to our guests. Thank you both for coming onto the show and for talking to me about maths and about the number 7. I've had a lot of fun. Before we go, though, I'm sure that many of our viewers would want to hear more about you and projects that you might be working on. Christian, let's go to you first. Do you want to tell us where people can find out more about you and what you're doing?
Okay, so this time you introduced me as a mega grant winner. So the project I'm doing for that is called Beach Spectres. The plan is to go down to the beach, just outside my house, really.
Hooray!
Take some Spectre monotile shaped cookie cutters, really big ones, and produce the aperiodic tiling on the beach as big as we possibly can. So that's going to happen next year, early summer. You can go to beachspectres.com to get more information about it.
Beachspectres.com. Thank you very much. I'll make sure that is in the show notes for people to have a look at. Khensanii, where would you like to direct people to?
So as I was introduced, I am a math enthusiast. I'm very passionate about math. I think people can follow me on Instagram. Yeah, on kran.chi. Yeah, I'll be posting stuff related to mathematics. I'll make tutorials. I haven't even posted, but yeah, I'm going to start making content there. So yeah.
Fantastic. Links in the descriptions as well. For me, if you want to find out more about what I'm doing, you can find me on Blue Sky at mathematicians-pod. And that is because I also do a small podcast about mathematics history. So if you want to know more about ancient mathematicians, I've now got 50 episodes published. You can go and check those out. They will help you fall asleep. The other big thing I want to plug, though, is the project I'm working on and most passionate about, which is this project right here, the Unnatural Numbers chat show. The purpose of this is to make a platform for anyone and everyone who wants to have a go at doing public speaking, possibly for the first time. So if you have been inspired by today's show and want to come on and present something and have a go at doing some public speaking, get in touch with me on Blue Sky, or you can follow the or you can fill in the form below in the description to get in contact with me that way as well. I'd love to have you on the show next time. Until then, though, bye-bye. Bye-bye, everybody.
Goodbye.
Bye.